When it comes to composition of two functions, we have to be very careful with a couple of things. First of all, if there's any values in the domain of f or the domain of g that are not allowed anytime within either one of those, we have to consider that the composition of those two functions also has the same domain. The domain of g carries over to f of x. The domain of f of x carries over to g. So in composing those two, if there's a number that stops the process, doesn't matter what the final result looks like, I can't use those values. It's a restricted domain, so I have to take those values out of it. So any x that is allowed into g of x will then be allowed into f of x. And likewise, any value that's allowed into the f of x equation is allowed into the g of x equation. And for that matter, when I do the composition of those two, if there's any that I have to take out, doesn't matter what the equation itself looks like when we're done. If at any point those values produce a restriction, we have to also consider that those values will not be included in our domain anywhere in the process. So let's take a look at this situation that does restrict a domain of f and g of x, but this time we're not really dealing with f of x, g of x, but it's an application that talks about the number of bacteria in refrigerated food. The number of bacteria is given by an equation. Let's just say, and I guess this is theoretical, it's not an exact equation, of course, but let's say that we observe that the number of bacteria, n of big T, is equal to 20t squared minus 80t plus 500, as long as big T is between 2 and 14. And big T is the temperature of the food in degrees Celsius. Now again, 2 is just above 32 degrees Fahrenheit for us, and then 14 is a little, it's close to about 50 or 60. 20 degrees is 68. So when the food is removed from refrigeration, the temperature of the food then is given by another equation. The temperature of the food in terms of little t is 4t plus 2, as long as little t is between 0 and 3, where t, well, little t is the time in hours. So find a composition of n of big T of little t and interpret the meaning and context. So if we're just talking about what does that really mean? Well, this is the number of bacteria as a composition of the temperature of the food in respect of time. Now keep in mind the time where it's out of the refrigerator is between 0 and 3. And the temperature of the food is between 2 and 14 degrees Celsius. Again, that's when the food is cold enough, and then it gets to just short of room temperature at that point. And it takes about 3 hours or so to get, according to these equations, about 3 hours. Then the last thing we're going to do is we're going to find the time when the bacteria count reaches 2,000. And in this situation, a bacteria count of about 2,000 is when the food starts to become unsafe for consumption. Probably sooner than that with some foods, but at 2,000, probably going to stay away. So how do we approach a question like this? First, we have to find the composition of n of big T of little t. So the number of bacteria as a function of the temperature of the food in respect of time. What does that look like? So if you want to give this one a shot, by all means, let me go ahead and get you started. We are substituting, as you notice. Big T of little t goes into the n equation for the number of bacteria. That is 4t plus 2 gets replaced into big T. 4t plus 2 gets replaced into big T. And then we're going to clean that up. So 4t plus 2 squared is a FOIL problem. And if we fast forward on that one, it's really just 4t times 4t, which is 16t squared. Multiply those two together becomes 8 and then double. So 16t plus 4. But that still has a 20 on the outside. Then minus 80. Not going to do anything just yet for the same reasons that I didn't multiply the 20. Just kind of carry the rest over for now. On the next step, And again, if you want to try these out, just pause and then you can continue and then see what you come up with. The first step might have been a little more difficult with the composition, but at this point I think you can finish this up and see if you come up with the same answer. So distribute. 20 distributed minus 80 distributed. Don't forget to take the negative with the 80 when you multiply it out. And then plus 500 because there's nothing to distribute that or to that. So that's going to just kind of carry along. Clean up a few things. Very conveniently, we notice plus 320 minus 320. That was nice of them. And so 320t squared plus 80 minus 160 plus 500. So 580 minus 160. Might be easier to do it that way. And so this is our new composition. That is the number of bacteria in the food after so many hours. Now remember, the hours in which the food sat out is up to 3 hours according to our restrictions. So then the second part of that question was, at what time will this reach 2,000 count for the bacteria? How do we find that out? Well, remember, this is N of T. This is the number of bacteria based on the temperature of the food in respect to time. So we set the whole thing equal to 2,000. And we solve. Luckily, this does not have any linear terms, so solving this is not going to be extremely difficult. If you want to try this out, go for it. Pause the video. If not, let's take a look at the answer. So minus 420 minus 420. So this is 1580. And that's equal to 320 t squared. Divide by 320. That is t squared is equal to t squared, and I'm just writing the t squared first just for, convenience. It's going to be about 4.9. So 15 divided by 3 is almost 5. So if you get something close to that, you can even almost just use 5. But I would not start rounding just yet. But if you go to your calculator, you'll find out you get 4.9375. But I don't want t squared. I want just t. So I take the square root of both sides. I took the square root. Don't forget, that means we have to consider plus or minus. But do we have to this time? We don't, because it is, in fact, time we're dealing with. So take the square root. I find out it's 2.22. And what are the units here? Hours. So when does the bacteria level reach 2,000? At about 2.22 hours. So then you're thinking, okay, 2 hours, the food's sitting out, about 2,000 on the level of bacteria according to this situation. Yeah, I mean, most people don't leave food sitting out for 2 hours and then just keep eating, right? Because we don't normally go to buffets or anything, right? And that's really what happens if the food is just sitting out and is just basically left to, just the elements. Bacteria level grows when it's not refrigerated. So about 2 hours after the food has been removed from the fridge, bacteria growth starts to get a little out of hand. One last thing for us to kind of take a look at. We are looking of f plus g of x. What does that look like when I add those two things together? X divided by 2 and then square root of x. So I'm adding these two together, right? Keep in mind, I'm adding two things together. I can only add together the portions of this graph that are defined. So is there any restriction to my domain here? X over 2? No. Square root of x? Yes. So when I go to add these two, I can freely graph x over 2. My graph for that looks like this. X over 2, so 0 over 2, 1 over 2, 2 over 2, which is 1, 4 over 2, which is 2, has a slope of 1/2, negative, negative, and so on. So f of x over 2 looks like this. Kind of crooked, but what does g of x look like if it's the square root of x? Remember, that's one of our parent functions. This one was the rocket, square root of x, square root of 1 is 1, square root of 0 is 0, can't get into the negatives. 1, 2, 3, 4 is 2. Actually, I did one too many. So this one looks like this. If I'm supposed to add those two graphs together, well, I can only add the portions of the graph where it's defined. So when I put red plus, blue, when I add these two things together, this graph cannot go into the negatives. The combination of those two has to start at 0 where it's defined. I can't add, oh, this value here, just add to nothing, right? Well, it's not adding to 0. So because there's nothing to add, I can only use 0 and above. 1, 2, 3, 4, 5, 6, 7. Probably don't need more than that. So let's look at those points that I plotted here. For this one, I have a 4, 2, and for this one, I do have a 4, 2 as well. So there's a point they have in common. Nice. 0, 0, the first one is 1, 1 for the red, and it's 1, 1/2. So 1, when I add those two together, becomes 1.5. Then, at 2, let's go to 4. At 4, it's 4, 2, and 4, 2, so it becomes 1, 2, 3, 4. 2 and 2 is 4. And so my graph starts doing a little something like this, and so on. And it's going to start, it doesn't curve that much actually. It's going to start at some point looking a little more like a linear equation. That is, if you take a closer look, let's put these on the same graph. 1, 1, and 4, 2. Here's the red. Here's the blue, and I'm only using the portion of the blue that is defined for both of these. And these two add together. Which one contributes more from 0 to 2? So let's divide our graph from 0 to 2. And then the other one is greater than 6. 1, 2, 3, 4, 5, 6. How do we know which one is contributing more? Well, it's which one has a higher function value. So between 0 and 2, looks like red has more function values. But more than 6, if you notice beyond 6, the blue, or f of x, has more function values to it. So it's taller in that section of the graph. All right. I do want to take one last look at something with you. I want to take a look at how do these look on Desmos. So let's go ahead and graph, and I'll show you again why that does not provide anything in the negative section as well. All right, so here we are with those three equations. I went ahead and put those in for you so we can take a look at y1, and I named them differently so we can actually just add those two. So y1 is x over 2, and we graph that. Oh, there's a purple line. They don't use the same colors, doesn't matter. So here's the line with a slope of 1/2. Then here is, let me turn that one off. Here's the line with the square root of x, and notice this one, just like we mentioned, looks like the rocket, right? But then I'm going to take both of those and combine them. I'm going to add those together, right? But notice, yeah, the purple has something here in the negatives. The black line does not have anything in the negatives. So, but wouldn't that just say, okay, I'll just add whatever I want down here because it just doesn't have anything to add to, so that's just going to contribute everything, right? Well, it's that restricted domain. I cannot add it. I cannot combine functions together if in part of one it's not defined. So notice how here there's no values on the negatives when I try to add these two together. All right, so yeah, it starts off like, oh, a little bit of a rocket, then it just looks like a linear equation closer and closer to it. It is curving ever so slightly as it increases, but not as much as you know, doesn't have that steeper x change as the square root does. All right. So just to finish off that lesson, you do have a homework assignment. Not too many to try out, just because some of these can get a little more involved. Number 57 is likely going to be, and I can tell you right now it is, a real life application type problems. I always like ending the lesson that way, so you can kind of see, where does this like really come into play? How can I apply this to a more realistic type situation? Probably not what you're going to be doing, let me do some math to calculate some bacteria, but you can see where it can be done. Homework again is to be done on WebAssign. Take a look there. It's the same problems. It's just in a platform where you can just literally just submit right there. But this is your textbook reference, and these are the problems that you have been assigned. If you have any questions, bring them next time.